Hi everyone, so today we're going to be learning about perfect squares and monotonically increasing functions. And more importantly, we're going to talk about the idea of bounding. It's a really interesting thing and it's actually really helpful to solve a lot of number theory problems. So let's see how that goes. So this is a question on the Australian Mathematical Olympiad from the year 2003. And in this video, we're going to be looking at primes and perfect squares. We're also going to be looking at the idea of the bounding, like I said before. I'll explain a little bit about that later. Then we're going to look at monotonically increasing functions, a little bit of calculus. After that, we have some book sessions for National Math Olympiads, and at the end, a similar challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what do we need to find over here? So we need to find all primes p such that this given quantity 5 raised to power p plus 4 times p raised to power 4 is a perfect square. So basically 5 raised to power p plus 4 times p raised to power 4 needs to be n square for some, let's say, natural number n, right? And what thing can we do? Well, there are like very common ideas. Let me just like highlight a couple of ideas to you. So whenever we have this sort of Diophantine equation like this involving powers, exponents and all, the first thing that probably comes to my mind is reduce mod n, right? Reduce mod n, but since we have maybe some primes, try and reduce mod p. Or maybe if you think that maybe something like mod 3 can be helpful, you can go for that as well. But maybe since primes are given, reduce mod p, or maybe let's say try a little bit of the Fermat's little theorem, because 5 is also a prime and p is its exponent. So this kind of like comes to my mind. The second thing that can happen to me is what we are discussing in this video, and that's called bounding, right? So bounding basically where you need to form an inequality, and this is the rather standard procedure. So the idea of the bounding is maybe form an inequality, after which it can never be a perfect square. So for example, let's say 4 is for p, 5 is for p plus 4 times p is for 4. Maybe form an inequality involving these things. Let's say that it is always maybe less than 0 for p greater than certain value. Right? Something like that. This is just a very rough idea. But try to maybe form certain inequalities and try to like make some certain claims and then actually prove that okay, beyond this prime, it can never be a perfect square. Or try to form certain inequalities that, for example, this might lie between two perfect squares. So it can never be itself a perfect square. Something like that, right? That's called bounding. So yeah, maybe let's just jump right into this and let's see how this goes. So okay, 5 raised to power p plus 4 times p raised to power 4 is equal to n square. What I see is that this is a perfect square and this entire thing also a perfect square, and difference of squares can be easily factorized. So let's just do that. So I send 4p raised to power 4 the other side. So this can be written as 5 raised to power p is equal to n plus 2p whole squared and n minus 2p whole squared. Actually not whole squared, it's just 2p squared, right? Sorry about that. So n plus 2p squared and n minus 2p squared. Okay, great. Now what next? Well, once I've gotten up to this, I can maybe just write something like n minus 2p squared will be equal to 5 raised to power k, and n plus 2p squared will be 5 raised to power l. And it's pretty easy to see that k plus l is equal to p, which just follows from the laws of exponents. Okay, great. So how can we proceed? Now what I can do over here is maybe the idea is to eliminate n, because n is a quantity that we had ourselves introduced. So maybe let's try to eliminate them in this equation over here. So maybe if I just subtract both the equations, I'll get 5 raised to power l minus 5 raised to power k is equal to 4 times p squared. And I think it's pretty clear to see that k will be less than l, right? Okay, great. Now we have this equation, right? So maybe let's just try and reduce this modulo 5. So when I try and reduce this maybe modulo 5, the left hand side is congruent to 0 mod 5. And obviously we're assuming that k is non-zero over here. Okay, because if one of them is 0, the thing's like kind of break up a little bit, and we'll just discuss that in a separate case. Now, the left hand side is 0 mod 5. So 4p square also has to be 0 mod 5. Right? So that essentially means that p has to be 0 mod 5. And since p is a prime, p has to be 5. Right? Because there is no other prime which is 0 mod 5. No other prime. Okay, there are numbers, but none of them are primes. So p is equal to 5, and what was our question? That 5 raised power p plus 4 times p raised power 4 is to a perfect square. Maybe just plug in p is equal to 5 over and let's just check if it is actually a perfect square. So this becomes 5 raised power 5 plus 4 times 5 raised power 4. So you can take 5 raised power 4 common. You'll get 5 plus 4. So you'll get 5 raised power 4 times 3 squared. 5 plus 4 is 9, which is 3 squared. So you can easily see that this can be represented as 5 squared times 3 whole square, or in other words 75 squared. So p is equal to 5 is actually a valid solution. So this is when k is not equal to 0, right? Now what is when k is equal to 0? So we had formed this equation 5 raised power L minus 5 raised power k is equal to 4p squared, right? So now let's just maybe analyze when k is equal to 0. What happens when k is equal to 0? So 5 raised power L minus 1 is equal to 4p squared, right? And since k is equal to 0, we had also noted that k plus L is equal to p. So therefore L becomes p. So 5 raised power p minus 1 is equal to 4p squared. So the entire equation is now just in one variable p. And now I can maybe like just write this as 5 raised power p minus 4p squared minus 1 is equal to 0. And now we use the idea of something called as maybe bounding, right? Maybe let's just try and make some claims for this. Now if we consider a function, now consider the function f of x such that f of x, maybe if I define it as e raised to the power x minus 4x squared minus 1. The idea is to kind of like form something similar to this, right? And I have replaced p with x, except for the fact that we have this e raised power x instead of 5 raised power x. And the reason I did that is, well, you'll actually come to know that soon. So I can actually say that f of x is going to be less than 5 raised power x minus 4x squared minus 1. This is the kind of the bounding idea that I was talking about earlier. And why is this true? Because e is actually 2.71828. So e raised to the power x, or this quantity, is obviously going to be less than 5 raised to the power x. And the other terms are the same. So it's pretty clear that f of x is actually less than 5 raised to the power x minus 4x squared minus 1, which is actually something similar to what we have in equation number 1 over here. Okay, great. So maybe how can we proceed? So maybe let's just try and calculate the value of f of 9. So what will the f of 9? It will be e raised to the power 9 minus 4 times 9 squared is 81 minus 1. So f of 9, what will it be? It will be, if it's try to maybe like approximate it or something, it will be actually greater than 2 raised to the power 9 minus 324 minus 1. Because e is like a little bit more than 2, it's 2.71828. So this is obviously greater than this quantity 2, right? So f of 9 will be greater than, I believe this is 2 raised to the power 9 minus 325, which is actually greater than 0. 2 raised to the power 9, if I'm not wrong, is 512, right? So therefore I can see that f of 9 is greater than 0. Okay, great. Now what can we do? So maybe let's make a claim. So my claim is f of x, which is equal to e raised to the power x minus 4x squared minus 1. So f of x is greater than 0 for all x greater than or equal to 9. In other words, f of x is strictly increasing in this interval, right? For all x greater than or equal to 9, or from 9 to infinity. And there's a pretty standard way to prove this actually involving calculus. So what will be f prime x? Well, you just differentiate this function. You get e raised to the power x minus 8 times x. Okay, great. So what will be f prime 9? It will be e raised to the power 9 minus 72, and it's obviously greater than 0, right? So f prime 9 is greater than 0. Okay, great. Now what is f double prime x? Well, let me just differentiate this again. You'll get e raised to the power x minus 8. And again, obviously, it's easy to see that f double prime x will be greater than 0 for all x greater than or equal to 9. So therefore, f of x is increasing in a given interval. So f of x is increasing. So therefore, strictly increasing rather, because it's greater than 0 for all x greater than or equal to 9. Now, what was the purpose of doing all of this? Well, what's our function? So f of x was what? E raised to the power x minus the other term, right? 4x squared minus 1. So we noted that f of x is greater than 0 for all x greater than or equal to 9. Now we also noted that f of x is less than this quantity, right? So in other words, if f of x is greater than 0, this quantity also has to be greater than 0, right? Because something like this inequality is being established. So 5 raised to the power x minus 4x squared minus 1 will be greater than 0 for all x greater than or equal to 9. But what do we want to find? We want to find 5 raised to power 4 minus 4x squared minus 1 is equal to 0, right guys? Because here we want it to be is equal to 0. But what we're actually seeing is for all x greater than or equal to 9, this is actually greater than 0. It never holds true, right? So 5 raised to power x minus 4x squared minus 1 is equal to 0 only holds for x less than 9, right? Or x less than or equal to 8. But since we have the prime p, so this will only hold for primes less than 9. So this can only hold for 2, 3, 5 and 7. P is equal to 5, we have already checked. So all you really need to do up till this point is now maybe check for P is equal to 2, 3 and 7. And I'll leave that up to you because it's really easy to just plug in. All you really need to do is plug it into this and check if this actually becomes a perfect square or not. And let me just tell you, it does not, right? Plug in 2, 3, 7. It is not a perfect square for any of these values. So therefore, P is equal to 5 is the only solution. So let me just maybe recap what we did over here. So I just started out with this expression. I factored it, pretty standard thing that we've done. And maybe just split it up into 5 raised to power k and 5 raised to power l. And after that time I just reduced mod 5 for the case that k is not equal to 0. And then we see that p is 0 mod 5 and p is a prime, so p has to be 5. Right? And p is equal to 5 is the only solution for k non-zero. And for k is equal to 0, we have this beautiful expression 5 raised to power p minus 1 is equal to 4p squared. And to solve this Diophantine equation, we use the idea of bounding. We actually consider a function that was less than the function that we have over here in equation number 1. And we showed that function is actually greater than 0. So this given function 5 raised to power p minus 4p squared minus 1 has to be always greater than 0 for all primes greater than or equal to 9. So therefore we just show that the only solutions can be possible when you have primes 2, 3, 5 and 7. P is equal to 5 obviously satisfies like we've seen before, and 2, 3, 7, none of them satisfy just by plugging in. So yes, that's quite an interesting problem, and I hope you learned something from that. Okay, so moving on with some book sessions for National Mathematical Olympiads, Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Problems in Plane Geometry by Sharagan, and Elementary Number Theory by Sierpinski. Okay, so at the end of a similar but challenging problem, and it's actually the construction is quite similar. So earlier we had 5 raised to power p plus 4p raised to power 4, and I gave you a couple of ideas. One was the idea of bounding that we followed over here, and the other idea was reducing mod n, right, or reducing mod p, because p is a prime over here. And here we need to find all primes p so that this given quantity is a perfect square. So we try this out using the ideas that I mentioned over here, and if you're able to solve it, let me know in the comment section. Until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.